To run a modern, multi-billion parameter language model, you're dealing with massive scale. We're looking at racks of enterprise GPUs processing immense matrices. Yet the same 70 billion parameter models load onto a local workstation for standard inference. The weights fit on consumer hardware, and the model generates text. But toggling that setup from inference to fine-tuning triggers immediate system failure. You instantly hit an out-of-memory error. These memory failures are typically attributed to the sheer volume of billions of model weights. The actual memory overflow originates in the auxiliary data structures required to maintain the training loop. The true bottleneck of AI adaptation is not the model size. The real barrier is the architecture of the optimizer state. During fine-tuning, a trainable parameter requires 4 allocations: the base weight, W, the gradient, and 2 running moments. These are mandatory for the Atom optimizer. Because of these states, peak memory reaches 20 times the parameter count, exceeding consumer hardware limits. Parameter-efficient fine-tuning, or PEFT, was engineered as a structural countermeasure to this specific multiplier. The objective is to shift the optimizer state's footprint from tracking every parameter, big P, to a tiny subset, little p. While freezing most of the network happens, the primary goal is minimizing active trainable parameters. To function effectively, a PEFT architecture must reduce active parameters while remaining capable of capturing the complexity required for task adaptation. A 2024 survey by Lilene et al. Organized over 30 of these parameter-efficient methods into 3 fundamental families. The first family, addition-based architectures, includes methods like soft prompts and adapters. These insert small feed-forward networks between existing pre-trained layers. Because these insert physical layers, they penalize the forward pass. Each token generation cycle must process these extra modules, which introduces unavoidable inference latency. The second family, selection-based architectures like BitFit, isolate a tiny fraction of existing weights, such as the biases, freezing the rest. While avoiding changes to the network shape, they rely on unstructured sparsity. This is computationally inefficient on GPUs, which are optimized for dense matrices. This creates an engineering trade-off. You must either accept serving latency with addition methods or sacrifice training efficiency with selection methods. A successful architecture must enable efficient training on dense hardware while serving the model with 0 added latency. Reparameterization-based methods were developed to address both sides of this performance trade-off. LoRa is currently the dominant architecture within this family. Instead of updating the entire original weight matrix, W, LoRa learns an isolated targeted update matrix called delta W. LoRa factors the full delta W update into 2 small matrices, W down and W up. This shrinks the trainable footprint to 2 times D times rank R. Atom only tracks these, collapsing memory state. Post-training, they multiply to recreate the original delta W shape. Because delta W exactly matches the dimensions of the original weight matrix, the 2 are added together into a single identical footprint. Since the weights are merged, there are no additional layers to calculate during the forward pass, unlike adapter-based models. LoRa's matrix mergeability provides parameter-efficient training without any inference penalty. This raises a question of efficacy. Can such a small update volume actually yield competent task adaptation? The theory is intrinsic SED, established by Aghajanyan in 2020. It proves fine-tuning is an intrinsically low-dimensional process. Because the model has foundational knowledge, adaptation only requires navigating a narrow subset of parameter space. LoRa's low-rank structure aligns perfectly with this required narrow update. LoRa is effective because it reflects the underlying physics of how pre-trained neural networks learn specific new tasks. Moving from theory to practice, we can look at the empirical findings from the Lilene et al. Benchmarking study. The survey tested 14 PEFT methods across 5 distinct datasets, scaling model sizes from 700 million to 11 billion parameters. Under strict constraints on hyperparameter tuning and training epochs, LoRa remains an exceptionally difficult baseline to outperform. Newer architectures frequently fail to exceed LoRa's performance when they are tested without excessive compute budgets or extensive training time. Benchmarking also revealed that layer norm tuning and BitFit remain competitive, even when adjusting less than 0.1% of the model's parameters. The study also highlights a reporting problem, where focusing only on trainable parameter counts severely understates the actual memory and compute costs in production. In constrained environments, the stability and mergeability of established methods often provide more value than newer, fragile architectures. There is a final, practical limit to consider. A measurable performance gap still exists between PEFT and full parameter fine-tuning. However, the 20x atom optimizer penalty makes full fine-tuning computationally inaccessible for most local practitioners. PEFT mitigates the optimizer state problem. Intrinsic SAID justifies the low-dimensional approach, and LoRa makes that approach mergeable. Today, the synergy between PEFT and quantization enables the adaptation of large open models within the memory constraints of a single local GPU. While scale is a defining factor in AI performance, understanding the low-rank mathematics of adaptation is what makes that scale accessible to the individual engineer.